Hello and welcome. In this notebook, we'll cover clean code and how we can write better codes. This is the part 1 of this series. Python has been used to demonstrate example codes. In this course, we will cover Chapter 1, Introduction, what clean code is, why it matters, and the cost of bad code. Chapter 2, Meaningful names, how to choose clear and helpful names. Chapter 3, Functions. Make functions small, clear, and focused. Chapter 4, Comments. Use comments only when they add real value. Chapter 5, Formatting. Organize code with clean structure and spacing. Chapter 6, Objects and Data. Follow good object design and limit knowledge sharing. Chapter 7, Error Handling. Handle errors clearly using exceptions and guard clauses. Chapter 8, Clean Classes. Keep classes focused, simple, and well organized. Let's get started. Introduction to clean code. What is clean code? In this slide, we explore the meaning of clean code. Clean code is code that is easy to read, easy to understand, and easy to change. It communicates the programmer's intent clearly, like telling a story to someone else. Clean code avoids unnecessary complexity. It is structured in a way that is predictable and consistent. It avoids duplication and sticks to clear naming rules. A clean code base is easy to test and debug. In short, clean code puts readability and maintainability first. It may not look fancy, but it is built for humans, not just for machines. Why clean code matters? Because it saves time, money, and effort over the life of a project. Clean code reduces the number of bugs and makes debugging much easier. It speeds up development, especially as the code base grows larger. Clean code is easier to test and easier to extend with new features. It helps team members understand each other's work. When new developers join the team, they can get started faster. Most importantly, clean code reduces the cost of maintenance, which is usually the largest part of any software project. In short, clean code is an investment that pays off again and again. Cost of bad code. Writing bad code may seem fast at first, but the cost adds up quickly. Bad code increases the number of bugs, which leads to more problems in production. It makes future development slower and more expensive. Bad code is hard to test and hard to debug. It can frustrate developers, reduce morale, and even cause team members to quit. Bad code often causes poor software performance and creates something called technical debt. Technical debt means extra work in the future just to fix old problems. In extreme cases, bad code can even cause a project to fail or a company to lose business. So remember, bad code is always more expensive in the long run. Characteristics of clean versus dirty code. Now let's compare clean code with dirty code. Clean code is easy to read and easy to understand. It uses clear and descriptive names that explain the purpose of each variable and function. Functions in clean code are small and focused on one task. The style is consistent, meaning things are named, spaced, and structured the same way throughout the code. Also, clean code avoids duplication. If something is repeated, it gets turned into a reusable function. Dirty code is the opposite. It's hard to read and confusing. It uses poor or misleading names like X or temp1, which give no clue what the variable is for. Functions are often too long and try to do too many things at once. The formatting is inconsistent. One part might use tabs, another spaces, or different naming styles. And worst of all, logic is copied and pasted everywhere, making bugs harder to fix and changes risky. Let's now look at a code example to make these differences more clear. Let's compare two versions of code that do the same thing. The first one is dirty. The function is named just the letter D, which tells us nothing. The parameters A and B are not descriptive. The formula is unclear. and it uses numbers directly without any explanation. This kind of code is very hard to maintain or reuse. Now look at the clean version. We renamed the function to calculate monthly interest. The variables are named clearly: principal amount and annual interest rate. We created a constant called months in year to replace the number 12. We also used math.py instead of a magic number. Now the code tells a clear story. It's easy to understand and update if the formula changes. Meaningful names. Choosing descriptive and unambiguous names. In this slide, we focus on choosing descriptive and unambiguous names. Good names make code easier to read and understand. They should clearly describe the purpose of the variable, function, or class. Avoid short forms or abbreviations like CNT, TMP, or val. Instead, use full and meaningful words. Be specific. For example, say user login attempt count instead of just data. If your code is in a certain domain, use domain-specific terms. For instance, in a banking app, use words like account, balance, or transaction. Clear names reduce the need for extra comments because the name itself explains the code. Let's compare poor and good naming with a real Python example. In the poor example, the function is called just the letter C, and the variables are x and y. This tells us nothing about what the function actually does. We can only guess by reading the implementation. Now look at the improved version. The function is named calculate total price, and the parameters are unit price and quantity. Now the code clearly tells us that we are multiplying the price of one unit by the number of units. We don't need to look at the function body to understand its purpose. This is the power of good naming. It makes code readable like plain English. Naming conventions are rules that help keep code consistent and readable. In Python, we follow a common style guide called PEP8. It recommends using snake case, that is, lowercase letters with underscores, for variables and function names. For example, use total amount or calculate tax. For class names, use Pascal case, where each word starts with a capital letter and no underscores. For instance, use user account or payment processor. Constants should be written in all capital letters with underscores between words. For example, max users or default timeout. The key is consistency. Pick a style and use it across your entire project. This helps every developer on the team understand and write code in the same way. Avoiding misleading names. One of the worst things in code is a misleading name. A name might look harmless, but actually hide what's really happening. Avoid names that are too generic or vague, like data, temp, or info. These names tell you nothing about what the variable is used for. Never reuse the same name for different purposes in different places. This creates confusion and makes bugs harder to find. Also, avoid using similar names for things that are not related. For example, don't name one variable user info and another info user. It may confuse the reader even more. Always choose names that reflect the actual job of the item. If the variable stores a list of items, call it item list. If it's a flag for logging, call it isLoggingEnabled. This helps other developers and your future self understand the code without guessing. Look at this code example. In the first version, we have a function named handle, and it takes a parameter called data. It loops over data using a variable called temp. But what kind of data is this? What does temp mean here? We can't tell. This is misleading. Now compare it with the clean version. The function is called display usernames, and the input is user list. Inside the loop, we use username to print each name. Now the purpose is immediately clear. This function shows a list of usernames. No need to guess. No need to read comments or go deeper. That's the goal of clean naming. Clear, direct, and self-explanatory. Use of pronunciation and searchable names. When writing code, remember, someone will need to talk about it. That someone could be you, in a meeting, or a teammate doing a code review. So, use names that are easy to pronounce. Avoid abbreviations like CFG, user, or tempi str. Instead, use full, clear words like configuration, user, or temporary string. Why does pronunciation matter? Because code is often discussed in conversations. It's hard to talk about a variable when you're not sure how to say its name. Now let's talk about searchability. Use names that are easy to find in the code base. A short name like A or X might appear hundreds of times, but a name like user profile photo path is much easier to locate. Also, stay consistent. If you use user profile in one place, don't switch to profile data somewhere else for the same thing. Consistency makes searching and understanding much faster. In short, names should be easy to say, easy to remember, and easy to search. Functions. Clean functions. Small functions principle. Clean code starts with clean functions, and clean functions are small, really small. In most cases, a good function is between 5 and 15 lines long. That's enough to do one specific task and do it well. Why keep functions small? Because small functions are easier to read, easier to test, and easier to reuse. When a function grows too big, it becomes hard to understand. It mixes multiple concerns, and bugs can hide in the complexity. If a function is doing too much, break it down. Create helper functions with clear names. Each helper should handle one small part of the task. The result is cleaner, more organized code. Remember, large blocks of logic should be sliced into bite-sized, understandable steps. Let's look at an example. In the first version, the function processUser handles everything by itself. It checks if the user is active, validates the email, and sends the message, all in one place. This makes the logic harder to follow and harder to test. In the clean version, we split the logic into smaller functions. We have isValidEmail to check the format and sendWelcomeEmail to send the message. Now, the main function, processUser, reads like a story. Each part is clear and self-contained. Smaller functions like these make your code easier to understand, test, and maintain. Clear function names. A good function name is one of the most important parts of clean code. It should clearly describe what the function does. No guessing, no reading the implementation. If the function performs an action, use an action verb in the name. For example, calculate tax, send email, or validate user input. These names are short, specific, and readable. Avoid vague names like handle, process, or worse, do stuff. These give no hint about the real purpose of the function. A strong function name should make comments unnecessary. When someone reads the function name, they should understand its role right away. For example, you don't need to write a comment like, "This function checks if the user is logged in," if the function is already named isUserLoggedIn. Finally, be consistent in how you name your functions. If you use get, set, or update in one place, use the same terms in similar cases across your codebase. Consistency builds trust and reduces confusion. Avoiding side effects. In clean code, a function should do only what its name says and nothing more. When a function has side effects, it does something extra that is not expected. For example, a function named calculateDiscount should only return a number. It should not also print something to the screen, write to a file, or update a global variable. These hidden changes are called side effects. They make code harder to debug, harder to test, and harder to reuse safely. Common side effects include modifying global variables, printing to the console, writing to files, or changing input arguments by reference. Clean code tries to avoid side effects unless they are absolutely necessary. We call such functions pure functions. They always return the same result for the same input, and they change nothing outside themselves. When you do need side effects, separate them from your main logic. For example, first calculate a value in a pure function, then print or store that result somewhere else. This separation keeps your code clean, testable, and predictable. Let's look at two versions of a function that calculates a discount. In the first version, we have a global variable called total discount. Inside the function calculate discount, we update this global variable. This is a side effect. The function does more than just return a result. It changes something outside of itself. This makes the function harder to test and reuse. Every time you call it, it changes the global state, even if you didn't expect it. If the function is called from multiple places, the global value may become unpredictable. In the clean version, we removed the global variable. The function now only does one thing. It returns the discounted price. There are no side effects. The function is now pure. That means it's easier to test, safer to use, and fully predictable. Function arguments. Clean functions have very few arguments, ideally 0, 1, or 2. When a function takes too many inputs, it becomes harder to read, harder to test, and easier to misuse. Functions with 0 arguments are the easiest to use. 1 or 2 arguments is usually fine, but if a function has 3, 4, or more arguments, it becomes confusing. The order matters. The meaning of each input becomes harder to remember. Mistakes are more likely. Instead of passing many arguments, try grouping related data. For example, if you're passing username, email, and age, you can pass a user object or a dictionary. Also, avoid using flags like do logging equals true. Flags usually mean the function is doing more than one thing. It would be better to split that logic into separate functions. In short, clean functions keep their input small, focused, and meaningful. This makes them easier to understand and much safer to use. In the first version, the function takes 4 arguments. It even uses a Boolean flag called sendEmail. This makes the function harder to understand and harder to use. You have to remember what each argument means and what the flag controls. In the clean version, we group the related user data into a single dictionary. Now the function takes just one input, user. Also, the welcome email is sent using a separate helper function. There's no flag. And each function does one job. This version is easier to read, test, and reuse. Fewer arguments mean fewer mistakes and cleaner function calls. Command query separation. Command query separation is a key principle of clean code. It means a function should do only one of two things, either perform an action or return information, but not both. A command changes state or performs an effect. For example, saving a file or writing to a database. Commands should not return values that are used for decision-making. A query, on the other hand, simply returns data or answers a question. For example, is valid user or get item count. Queries should not change the system or modify data. Mixing both creates confusion. If a function changes something and returns a value, it's unclear what its true purpose is. This can lead to hidden side effects and unpredictable behavior. By following command query separation, your code becomes easier to read, test, and reason about. Each function does one clear thing, either act or answer, but never both. Let's compare two versions of the same task. In the first version, we save a user and immediately return the number of users. This function is doing two jobs, saving the user and reporting the size of the database. This mixes command and query, which can cause confusion later. In the clean version, we separate these actions. The function saveUser performs the command. It adds a user to the list. The function getUserCount handles the query. It returns the number of users. Now each function has one clear role. This separation makes the code easier to test, easier to reuse, and easier to understand. Comments. When to comment and when not to. In clean code, comments are a last resort, not the first solution. The best code doesn't need comments because it explains itself through clear naming and structure. So, when should you comment? Only when the code cannot be made clearer without one. For example, if a function uses a complex algorithm, you might explain why it's used. That's valuable context. Don't comment to explain what the code is doing. If your code needs a comment to explain its behavior, you should probably rename the variables or break the logic into smaller, clearer functions. Also, avoid writing comments that state the obvious. Never leave outdated or misleading comments. If the code changes, update or delete the comment. Otherwise, it becomes a trap for future developers. In summary, comment only when necessary, focus on why, and prefer writing clean code that speaks for itself. Let's look at some code examples. In the first example, we see a comment that says, increment user count, but the line of code already makes that obvious. That comment is bad because it repeats the code without adding value. In the second example, the comment explains a business rule. It tells us why we are adding 1 to the user count, because each referral earns a bonus user. That is useful information that you can't get just by reading the code. Next, we see a variable named x, with a comment saying x is the value of pi. That's bad. A better solution is to rename x to pi. Now the comment is not needed at all. Finally, we have a good comment that explains a workaround for a known bug. This is a perfect use of a comment. It explains a necessary but temporary fix, and even references a bug ticket. The rule is simple. Bad comments describe the code. Good comments describe the reason. Legal, informative, and to-do comments. In some cases, comments are not just allowed. They're necessary. Let's look at 3 useful types of comments: legal comments, informative comments, and to-do comments. Legal comments include things like license headers, author names, or copyright notices. These are often required in open source or enterprise code, especially at the top of source files. Informative comments help clarify design choices that aren't obvious. They explain why something is done a certain way. For example, performance reasons, compatibility, or historical context. Then we have to-do comments. These mark unfinished tasks or parts of the code that need improvement later. They act like bookmarks for the future. Here are 3 examples of valid comments. First, a legal comment. It includes copyright information and the license. This is important in shared or open source code to define usage rights. Second, we have an informative comment. It explains why a tuple is used for immutability and performance. This helps future developers understand the reasoning behind the choice. Third is a to-do comment. It marks a place in the code that still needs improvement. In this case, switching from hard-coded values to a configuration file. To-dos should always be actionable and not forgotten. In summary, legal comments set rules, informative comments explain decisions, and to-dos help manage future tasks. Used wisely, they support clean and maintainable code. Code formatting and structure. Vertical formatting. Clean code is not just about what you write. It's also about how it's organized in the file. This is called vertical formatting or file structure. Think of your code like a story. The reader should start at the top and follow it smoothly, line by line. To help with that, group related functions and classes together. Keep logic that belongs together physically close in the file. Separate unrelated logic with space or move it to different files. There's a common order that helps with readability. Start with imports, then constants, followed by classes, then functions, and finally the main block. Also, try to avoid deep nesting, where blocks are buried inside blocks. And try not to make your files too long. A good rule is to have one main class or purpose per file. If a file is trying to do too much, it's time to split it. When your file is organized vertically, clean code becomes easier to read, understand, and maintain. Let's look at a good and bad example of vertical formatting. In the good version, we follow a clear top-to-bottom order. First, we import the datetime library. Next, we define a constant for the date format. Then, we declare the user class, followed by the format date function. At the very end, we add the main block with the program's entry point. This makes the file easy to scan and understand. In the bad version, the order is jumbled. The function comes first, then the class, and the import is buried at the bottom. Even though the code still runs, it's harder to read and harder to maintain. Good vertical formatting isn't just about style. It makes the purpose of your code clear at a glance. Horizontal formatting is all about how code looks from left to right, across the screen. Clean code avoids long, wide lines that require horizontal scrolling. As a general rule, keep your lines under 80 to 100 characters. This improves readability, especially on smaller screens or split views. If a line gets too long, break it into multiple logical lines. Do this in a clean and consistent way, for example, breaking after commas or operators. You can also use light alignment to make lists or dictionaries easier to scan. But be careful, too much alignment can make code harder to maintain. If you add or remove items, everything shifts and it becomes messy. In short, use horizontal space wisely. Short lines, clear structure, and light alignment help everyone read your code more easily. Let's look at a few examples of clean and messy horizontal formatting. In the first example, the dictionary is written in one long line. It's hard to read and hard to edit. The second version is much clearer. Each key value pair is on its own line, and light alignment makes it easy to scan. We can instantly see all the fields in the data. In the third example, we see a long expression. Instead of cramming it into one wide line, we break it across multiple lines. This keeps each part readable and logical. These techniques reduce mental strain. They help us see the structure of the code and understand its logic faster. So remember, shorter lines and clear layout mean cleaner code. Consistent indentation. In Python and in most programming languages, indentation is everything. Clean code uses consistent indentation to show the structure of logic. In Python, the standard is 4 spaces per indentation level. Not 2, not 8, just 4. Also, never mix tabs and spaces. Mixing them might look fine in one editor, but break completely in another. It also causes confusing errors in Python. Indentation is what makes the code readable. It shows you which block belongs where, whether it's inside a loop, a function, or a condition. Inconsistent indentation makes code hard to follow and can even crash your program. So always follow a strict and consistent indentation rule. A good editor or linter can help you catch mistakes, but ultimately, keeping your indentation clean is your job. Here's a clear example of good and bad indentation. The first version, the function and its logic are properly indented using 4 spaces per level. It's clean, easy to follow, and won't cause issues. But in the second version, indentation is all over the place. The if block has 2 spaces, else is over-indented, and print is under-indented. This makes the structure unclear. And in Python, this code may even fail to run. Always follow one rule. Indent every block the same way. 4 spaces, no tabs. This is one of the simplest ways to keep your code clean and reliable. Blank lines for readability. Clean code is not just about what you write, it's also about how it looks. And that's where blank lines come in. Use blank lines to separate blocks of logic and make your code easier to scan. Group related lines together and leave a space before a new section of logic. For example, leave a blank line between function definitions or between setup and execution steps. This gives the reader visual cues, like paragraph breaks in writing. But be careful, don't overdo it. Too many blank lines can actually make the code harder to follow. Avoid placing random or unnecessary blank lines. So remember, use blank lines intentionally. They're a simple tool to guide the reader and show the logical structure of your code. Here's how blank lines can completely change how readable your code is. In the first version, each function is separated by a blank line. There's also spacing between the function definitions and where they're called. This layout is clear, organized, and easy to follow. In the second version, there are no blank lines at all. Everything is crammed together. It's harder to scan and understand what the code is doing. Use blank lines to create structure and flow. Just like paragraphs in writing, they let the reader breathe. Clean formatting helps you and your teammates work faster and safer. Objects and data structures. Tell, don't ask principle. The principle we're learning here is tell, don't ask. In bad code, we often ask an object for data, then make decisions outside the object. This leads to procedural code and breaks the purpose of object-oriented design. Instead, we should tell the object what to do and let it decide how. We push the behavior into the object, not outside of it. This makes your code easier to maintain, easier to reuse, and better encapsulated. You don't need to know the object's internal structure. You just need to know the actions it can perform. So repeat after me. Don't ask for data and decide. Tell the object what to do. Let's compare two versions of a simple scenario, checking an order status. In the bad version, we ask the object for its status and then decide what to do. This violates encapsulation and spreads logic across the codebase. In the good version, we push the logic into the object itself. Now, the object handles the behavior. It hides the implementation details and keeps our external code clean. This is a key principle of object-oriented design. Tell the object what to do. Don't ask for its internals and act on them yourself. This approach keeps your code modular, testable, and future-proof. Encapsulation and abstraction. In object-oriented programming, two key principles are encapsulation and abstraction. Encapsulation means hiding the internal details of how an object works. It protects the object's state and behavior from being changed or misused externally. Abstraction means exposing only the relevant parts of an object. You don't need to know how it works internally, just how to use it. Think of a car. You don't need to understand the engine to drive it. You just use the pedals and the steering wheel. That's abstraction. The engine is encapsulated. These principles make code easier to understand, safer to use, and simpler to change in the future. Here's how encapsulation and abstraction look in practice. In the first version, the balance variable is accessed and changed directly from outside the class. This is risky. Anyone can change it to any value, even negative. In the second version, the balance is hidden using a private variable with an underscore. All changes go through controlled methods like deposit. This protects the data and allows you to add checks, logging, or limits later. Users of the class don't need to know how deposit or get balance works. They just use the interface. That's abstraction. So remember, encapsulate internal data and abstract the interface. This leads to safer, cleaner, and more flexible code. Data versus objects. In clean code, it's important to know the difference between data structures and objects. An object exposes behavior and hides its data. For example, it has methods to act on its own data, but you can't access the data directly. This is great for object-oriented design, where we want encapsulation and behavior in one place. A data structure, on the other hand, is just a container for data. It exposes its fields directly and typically has no behavior. This is more suitable for procedural programming, where logic is separated from the data. So, when should you use which? If you want to model a real-world entity with responsibilities, use objects. If you're processing raw data in a pipeline, data structures may be better. Mixing both without understanding their roles leads to bad design, so be intentional. Either model behavior with objects or process raw data with procedures. This example shows the contrast between a data structure and an object. In the first class, user data, the name and age are public. You can directly read and write them. There's no behavior, just storage. This is a data structure. In the second class user, the data is hidden, and you only interact with it through methods like greet. The object controls how its data is used. That's behavior plus encapsulation, a real object. Both styles are valid, but you must be consistent. Mixing data and behavior randomly can lead to confusing and fragile code. Use objects when behavior matters. Use data structures when you're simply passing information around. Law of Demeter, principle of least knowledge. The Law of Demeter, also called the principle of least knowledge, is a simple but powerful idea. It says talk only to your immediate friends, not strangers. In code, this means that a method should only call its own methods of objects it directly owns, or methods of parameters passed to it. You should avoid chained method calls, because you're reaching deep into the internal structure of other objects. This makes your code tightly coupled to the structure of other classes. If any class in that chain changes, your code breaks. Instead, ask the direct object to do the job for you. This keeps your code cleaner, simpler, and easier to maintain. Let's look at this example. In the bad version, we access order.customer.address.city. That's a long chain of calls, and it breaks the Law of Demeter. We are reaching deep into multiple layers of objects. In the good version, each class provides a method to return the city. The order class simply calls getCity and lets the inner classes handle the rest. This design follows the principle of least knowledge. Each class only knows what it absolutely needs to know, no more. As a result, our code becomes more modular, resilient to changes, and easier to test. Error handling. Clean and graceful error handling. In clean code, handling errors is just as important as writing the main logic. First, never ignore errors. When something goes wrong, your program should handle it, not crash or silently fail. Second, keep the error handling separate from your main logic. This makes the code easier to read and maintain. Good programs fail gracefully. That means if something breaks, the app doesn't explode. Instead, it shows a clear, friendly message and logs the error for later debugging. Never show raw error messages or stack traces to users. That's confusing and sometimes even a security risk. And always log errors with useful context. What happened, where it happened, and why it may have happened. Clean error handling protects your software, your users, and your sanity. Let's look at this example. The bad version simply opens a file. If the file doesn't exist, the program crashes and shows a scary traceback. That's not clean, and definitely not user-friendly. A good version uses a try block. If the file is missing, it catches the error and prints a simple message: "Sorry, the file was not found." We also check the result. If the content is missing, we inform the user and ask them to check the file path. This is clean, clear, and helpful, exactly how errors should be handled. Exceptions versus return codes. In programming, there are two common ways to handle errors: using return codes or using exceptions. Return codes are values returned by a function that signal success or failure, but they mix normal logic with error checking. It's easy to forget to check the return value, and this leads to hidden bugs. On the other hand, exceptions clearly separate the main logic from the error handling logic. They help you write cleaner, more readable, and more expressive code. That's why exceptions are preferred in modern programming languages like Python. Use return codes only in special cases. Otherwise, raise and catch exceptions. Here's a comparison of return codes and exceptions. In the bad example, the function checks for division by 0 and returns none. But the caller must remember to check for none every time. This can easily be missed, and bugs can sneak in. In the good example, we use Python's built-in exception. If division by 0 happens, the exception is caught, and we show an error message. This separates the logic from the error handling, making the code much cleaner and easier to maintain. When you use exceptions correctly, your code becomes more reliable and robust. Use of try, except, finally. In Python, we handle errors using try, except, and finally blocks. Use the try block to wrap code that might cause an error. The goal is to protect the code and react properly if something fails. Use except blocks to catch and handle specific exceptions, like a file not found or division by 0. You should always handle exceptions intentionally and give meaningful responses. Use finally when you need to clean up, no matter what happens. For example, closing a file or releasing a resource. The code inside finally always runs, even if an error occurs. Keep your try blocks short and to the point. This makes it clear which lines can fail and keeps the logic easy to follow. Most importantly, never catch errors and do nothing. Silent failure hides problems and makes bugs hard to trace. In this example, we use try, except, and finally to read the file safely. Inside the try block, we open the file and read its content. If the file doesn't exist, we catch the file not found error and print a clear message. We also catch any other unexpected errors just in case, and we print a description of the problem. Finally, the finally block makes sure the file is closed, whether the read was successful or not. This prevents resource leaks. The result is clean, reliable, and readable error handling. This is how good programs manage risk and recover safely. Avoiding deeply nested code. Deeply nested code makes programs hard to read and maintain. Each level of indentation adds visual noise and hides the main logic. Instead of writing nested if-else structures, use guard clauses to handle errors or edge cases early and exit. This keeps the main logic flat and easy to follow. Returning early is not bad practice. It's often the cleanest way to simplify control flow. So, when handling errors or invalid input, deal with them at the top and let the rest of the function handle the normal case. This improves clarity and reduces cognitive load. Let's look at two examples. In the bad version, each condition is wrapped inside the next. By the time we get to the real action, processing the order, we're 3 levels deep. It's harder to read and maintain. Now, let's look at the better version. We use what is called guard clauses. A guard clause is a quick check at the top of a function. If something is wrong or unexpected, we immediately handle it and exit the function early using the return keyword. So in the improved version, first we check if the order is missing. If so, we print no order found and return. Next, we check if the status is not equal to pending. If so, we print order not pending and return. Then we check if the amount is less than or equal to 0. If it is, we print invalid amount and return. After all these checks pass, we are confident the order is valid, so we print processing order. This version is flat, readable, and easy to follow. Each condition is clearly separated, and the logic is not hidden inside multiple indentation levels. That is the power of using guard clauses. Clean classes. Small and focused classes. In clean code, classes should be small and focused. That means a class should do one thing and do it well. If your class has many unrelated methods or handles multiple concerns, it's a signal that the class is doing too much. This kind of class is hard to test, hard to reuse, and often full of hidden bugs. Small classes are easier to understand. You can quickly read through them and know exactly what they are responsible for. They are also easier to change. When a class has only one job, changes in one part of the code base are less likely to break something else. If a class keeps growing, for example, handling database logic, user input, and file writing, it's time to split it into smaller classes. Each class should have a clear responsibility. Think of classes like cleanly organized tools. Each tool has one purpose: a hammer for hitting, a screwdriver for turning screws. Your classes should follow the same logic. Single Responsibility Principle, SRP. The Single Responsibility Principle, often shortened as SRP, is one of the most important ideas in clean code. It means that a class should have only one reason to change. In other words, a class should focus on just one responsibility. If your class is handling user interface, database logic, and validation all at once, then you are violating SRP. Each of those concerns can change for different reasons, and that makes the class hard to maintain. When a class follows SRP, it becomes easier to test, easier to read, and easier to modify without breaking unrelated functionality. For example, if the way we validate data changes, we should only need to touch the validation class, not the user interface or database class. Violating SRP often leads to tight coupling, where unrelated parts of the program are stuck together. This makes debugging and refactoring painful. By respecting SRP, you keep your codebase modular, clean, and adaptable to future changes. Cohesion. Let's talk about cohesion. Cohesion means how closely related the parts of a class are. In clean code, we want high cohesion. A highly cohesive class has methods and variables that all relate to a single purpose. It's focused, clear, and easy to understand. On the other hand, a class with low cohesion mixes unrelated responsibilities. For example, it might handle both file saving and user interface. This makes the code hard to read, hard to test, and hard to maintain. High cohesion means that everything inside the class works together to support one clear role. This improves code readability, makes testing easier, and promotes code reuse. If you find that a class is doing too many things or contains methods that feel out of place, it probably has low cohesion. In that case, split it into smaller, more focused classes. So remember, high cohesion is a sign of clean code. Each class should feel like a tightly focused team, not a random group of tasks. In this example, the first class is called User Manager. It handles 3 different responsibilities: validating a user, saving the user to a database, and sending a welcome email. This violates the single responsibility principle. Why? Because the class might change for 3 different reasons. 1 for validation rules, 1 for how data is saved, and another for how emails are sent. Now look at the second version. We have 3 small focused classes: User validator checks if the email is valid. User repository saves the user to the database. Email service handles sending emails. Each class does only one thing and has one reason to change. This makes the code easier to test, reuse, and maintain. This is the single responsibility principle in action. Class organization, fields, constructors, methods. A clean class isn't just about what it does, it's also about how it's organized. Well-organized code is easier to read, maintain, and debug. Inside a class, we should follow a logical and consistent order. Most developers expect a familiar structure. First, we define any constants or static values. Then come the fields, also called attributes or member variables. Next, we write the constructor, which sets up the object when it's created. After that, we list the public methods. These are the main actions the class offers. Finally, we include any private helper methods that are used internally. Grouping related items together and keeping this order across your codebase builds consistency. It helps other developers quickly find what they need. So remember, constants, fields, constructor, public methods. Then private methods. This is a simple rule that greatly improves readability and developer experience. In this example, we show a clean class structure. The class is called invoice processor. First, we define a constant called tax rate. It is written in all capital letters. Next is the constructor method, $_init. It initializes the customer and items fields. Then come the public methods, generate invoice and send invoice. Finally, we include private helper methods like calculate total and print invoice. They are marked with an underscore prefix and used only inside the class. The order is clear: constants, fields, constructor, public methods, and then private helpers. This consistent layout makes the class easier to read, navigate, and maintain. Thanks for watching.